This is Physics 2211, Lab 2, Motion of a Falling Object. So, brief overview, I'm going to go into the introduction, then I'll talk about some of the physics involved, then we'll look at the observed motion, and then we'll look at the computational models produced from the initial conditions of the observed motion. Then we'll compare the three models with each other, and then we'll look at some of the results that can be determined from these comparisons. And then finally, I'll go into some key takeaways about broader conceptual questions relating to this topic. Introduction. The purpose. So the purpose of this lab was to observe and record the motion of an object dropped from rest and compare the data taken from this observed motion with data produced by computational models. And these two models are gravity and gravity plus drag. Results preview. So the observed position versus time was more similar to that of the computational model that only factored in gravity than it was to the model that also factored in drag. This may be due to some error, but we'll get into this towards the end of the video. Physics involved. Fundamental principles and equations. So some of the important equations for this lab are F equals ma and F net equals the sum of all forces acting upon the system. In this lab, we are only accounting for the force of gravity on Earth and the drag force. The position update and velocity update formulas can both be derived from Newton's second law. Observed motion. So as you can see with our track, the paper ball is dropping from near the top of to the floor. The total time it took for this to happen was 0.43 seconds, and the initial velocity was 0.000 meters because we dropped the ball from rest. Its initial position was 1.020 meters as we dropped above the meter stick. The system in this lab is the paper ball and the Earth and the atmosphere that the paper ball is passing through. Computational motion. My first change was in line 39, where I took the position vector and changed it to be equal to the initial position of the paper ball. My next change was in line 44, where I changed the size of the time step to reflect, or so that it would reflect the number of steps in the observed model. In line 65, I changed the total time to be 0.433 seconds, and in line 69 through 76, I changed the value so that the code would reflect the relevant forces acting upon our system. In the gravity plus drag model, the only real changes I made were in line 56, where I updated the proportionality constant, and in line 69 through 72, where I updated the relevant forces for this model, respectively. Model comparison and results. Model comparison. Our observed model is falling at a greater velocity than the computational model for gravity. Notice that initially both computational models follow with each other very closely, but as time passes, the model with drag begins to deviate as air resistance comes into play. Also notice how the gravity model begins to catch back up to the observed model towards the end. Results. The observed model fell faster than both computational models. This is not what would have been expected because the observed should be less than the computational model with gravity because it is being affected by drag forces. This can be explained by the paper ball likely having some amount of velocity when it left the hand rather than it actually starting at zero as we assumed. The drag forces can be seen in the model because as time passes, the gravity model begins to catch back up to the observed data. Key takeaways. What does it mean? So we can see in the gravity plus drag model that it is approaching a terminal velocity due to the drag balancing out with the acceleration due to the force of gravity because as the velocity increases, air resistance increases. However, the gravity model is continuously increasing in velocity at a constant rate and therefore does not have a terminal velocity. What if? Even with an initial velocity of -1 meters per second, the models still appear to approach the same terminal velocity. Conceptually, this also makes sense because the initial velocity does not affect what terminal velocity force and the force of gravity will equal out at. A higher initial velocity will only lead to the forces balancing out more quickly. Thank you.